All right. Yeah, pet show and tell. All right, so welcome to class. Today there's not a warm up. We're starting something new. We're actually going to do a little bit less in this topic because obviously everything that's going on right now. So this will be our last topic we cover before we get to the test. So we're probably going to have a test some point towards the end of next week, maybe middle of next week, whenever we get a little bit more clarification on a few things. One thing I want all of you to go out and find is just some sort of plastic bottle. It's important that you be able to resonate the bottle like this. So you should be able to have a bottle that when you blow across the top, it makes a loud resonating noise. So you're going to need this for a lab you're going to be doing maybe at the end of this week, early next week, one of those two things. And MST, we're probably just going to turn that into your MST project. You're going to be making instruments out of bottles. All right, so try to get a bottle. Each person should try to get one. Just don't go out only to get a bottle. Just try to save one from around your house and wash it out cleanly. Water bottle should work as long as you can blow across it and it resonates and makes that loud noise. All right, so today we're going to be talking about waves on a string, specifically what are called standing waves. So all the waves we've been talking about right now so far are traveling waves, where you send the wave and it moves across. These are like ocean waves. So you send an ocean wave out and the wave moves all the way across the ocean until it runs into a shore. Today we're going to be talking about waves on a fixed string. And this is going to be kind of like a guitar string. So I have this set up here. We have a string right here. I have a motor right here that I can turn on that shakes the thing with a set frequency, because this is unbalanced right here. So we have a thing that can cause a frequency. We have a string that can be shaken, and then we have a mass hanging down here that can change the tension we pull the string with. Now, when we do this, if you have any sort of stringed instrument, how do you change the pitch of a string instrument? How do you tune a string instrument?
By tightening or loosening the string.
By tightening or loosening the string. So they have a thing right here, they turn it, they either make it tighter for higher pitch or less tight for lower pitch. Our tightening and loosening the string is going to be performed by adding different amounts of coins in here. So as I add more coins, I'm increasing the tension. All right, so I didn't have time to go through and tune this. More than that. So if I add just enough mass, we see that this thing is shaking in a certain pattern. So it's forming this certain shape here. So if I look kind of closely, I have points right here that don't move at all. See, the string is just staying stationary there. And at this end point, we have a point where the string isn't moving whatsoever. But in this middle point here, the string is moving back and forth really fast. Is everyone able to see this?
Yeah.
We get kind of a wave pattern right here in envelope. So there's a set frequency that'll do this and a set mass. If I say go and add a few more nickels to there, we see it's not as good. It's a little bit smaller pattern. And then as I add even more, it's further and further away from that value. And we get a point where it just stops occurring. So what's happening is that certain frequency and that certain amount of tension was creating the perfect amount of waves where it could resonate and cause a constructive interference. But if I change that, it's not resonating perfectly and I have destructive interference. So we're going to be doing a few notes here. And of course, my screen is flipped. So everything I do is reverse. So if I go the wrong direction, that's why. So we're going to be talking about standing waves on a string. All right, and this is what you can see in your homework is what we're going to be talking about. So standing waves on a string, I can only have so many set number of waves before this thing breaks apart. So this previous one, how many waves did I have there? So this one I saw here, it went kind of like this. It went down like this. So it was bouncing back and forth between these 2 points. How many waves do I have here? Is it a full wave?
It's one half of a wave, right?
It's one half of a wave. Yeah, sorry. Were people saying it? Yeah. So it's exactly half of a wave. So I have one half of a wavelength. Now, this is the longest possible shape that I can make on this. I can't make it any longer. It's limited by the length of the string, so I can't make this longer. So this is going to be the longest wave I can possibly have on this string, or what we're going to call our fundamental frequency. Or we can also call this our first harmonic. So this is the lowest possible frequency that I can use that will make this thing resonate with this amount. That'll cause this constructive interference pattern. Now, this is what most of your instruments are going to do if you're like this is let me rephrase that. This is going to be like the lowest possible frequency you can get off a certain string. So there's a reason why if you have, say, like a bass, they have really long strings, so they have really long wavelengths, which means they're going to have low frequency. So if you want a higher frequency instrument, you're going to shorten and shorten the instrument to have a shorter string, so you have shorter wavelengths. All right, so I can do this. I can get my first harmonic. I can't change my frequency on this thing easily without like shorting out some of the batteries. So instead of doing that, we're going to change the mass hanging off the edge here. Turn this back on. Not too much. All right, so if I change the amount of mass I have hanging on here, now I can see different amounts of patterns here. So now I see one part that's moving really fast, and another part that's moving back and forth really fast. And I have this spot right here in the middle that's just completely not moving. If I put my finger on, well, that specific point, it doesn't affect the wave. So I have 2 different patterns. So what did I change to do this? I added fuels hanging down off the edge. So we'll get into the equation that we're talking about here.
Is that destructive interference?
So, maybe I need to put a dime in there. Yeah, if you look in your lab, I needed different masses and I couldn't think of what to use, so I rated my coins in order to come up with masses. You were just working. Why don't you want to work now? Just a second. There we go. So yeah, so we have points where we thanks where we have destructive interference where the wave cancels out, but then we have points where we have constructive interference where the waves don't cancel out. So by changing the amount of hanging mass, I can change where this interference occurs. Focus camera. There we go. So we have these points here. So this point from here down to here, this is where we have the most constructive interference. And this point we're going to call our antinode. So where it's moving back and forth a lot really fast, that little blurry part is what we called our antinode. And then we're going to have these endpoints here where we have destructive interference. And this is what's going to be called a node. All right. So a few things we can get here. How many nodes do I have for the first harmonic?
2.
So the first harmonic, we have 2 nodes. And how many antinodes? This whole thing is just 1. Even though it's back and forth, this is just the same string. The string goes from here to here to here to here. So it's the same string moving back and forth. So I still just have 1 antinode. Now, I can look at this, my first harmonic. We're going to be talking about integers of here. So when we deal with integers, what letter do we use to signify an integer?
I.
Not I, because I is what we're using for imaginary number. It's, instead of x, we use x for variable. And we use n for an integer, right? So we can call this n equals 1. So we can see the number of nodes is going to be n plus 1, because I'm in the first harmonic and I add 1. But I have n antinodes. All right. But then we can jump down here. So this next one we got, let's move this slightly. How many waves was I able to get the second time I did this?
Wait, was the second one the second harmonic?
The second one is the second harmonic. Yeah, let's write this here. Second harmonic. How many waves was I able to get here?
1.
1. This is 1 full wave. It has a full up and a full down. So now I have 1 full wavelength. So how many wavelengths did I add going from here to here?
Half.
I added half a wavelength. So plus 1/2 wavelength. All right. So we're seeing that we're only able to get half wavelength intervals here. And this is actually really similar to what's happening in quantum mechanics. If anyone was wondering, the word quantized means you can only have a set number of values. So here we have like n equals 1, second harmonic. So we're going to call this harmonic. So we're going to have n equals 2. I have how many nodes?
3.
We have 3 nodes.
So n plus 1?
N plus 1. And then how many antinodes?
1.
1,
N.
2
N.
antinodes, right?
So it's n.
That's just n. And then I'm going to go a step further instead of just saying 1 wavelength. 1 wavelength is equal to the length of the string. Half a wavelength is equal to the length of the string. All right. So I get, yeah, second harmonic. And then the other thing is we're going to see the second harmonic. The other thing I can call this is my first overtone. So this is going to be the first possible resonance above my first harmonic. So the first time it resonates, that harmonic. So this is something about how, say, on a brass instrument, you can have the same keys pressed down, but you can play higher pitched notes. So it's similar to that, where you can have it resonating with more and more parts of the wave. All right, so let's make some predictions here. What do you think we're going to call this next time it resonates?
The next full resonation?
Yeah, so we called this one the fundamental, the first harmonic. The second harmonic, what is this one going to be?
The third.
The third harmonic, you can third harmonic. Which overtone?
Second?
Second. Yeah, exactly. We're just counting here. Second overtone. So this is the second time we resonate after that first harmonic. How many waves do you think we added going from here to here, then here to here? How many waves are we adding?
Half.
We're adding half of a wavelength, right? Because when we do this, the very end points here, this point has to be stuck in place. This isn't going anywhere. This point has to be stuck in place. This isn't going anywhere. So I have to add half of a wave in order to keep those two pieces stuck in place. Otherwise, it won't work. So we're going to add half a wavelength. So that means we're probably going to have something like this. Up, down, up. All right, so the third harmonic, so this is going to be n equals 3. How many nodes do I have?
4.
1, 2, 3, 4 nodes. So 4 nodes, just like before, that's n plus 1. And how many antinodes?
3.
3 antinodes. Three antinodes, and this is just going to be value n. So did I write everything? Yeah, that's good enough. So let's test this. So this third harmonic, I expect to happen. Now we're going to have to reduce the mass. So if this was an instrument, we would say reduce the tension. Now we have this. I took the masses out of this. Maybe I'll add one more. But now, look at that. We have our 3 little sections. Let me try adding just one. No. So we have our 1, 2, 3 little half wavelength packets. And there's nothing really stopping us from doing more. Let's try to do error. Keep getting close, but I don't have very steady hands. But yeah, we can have more. You kind of see it jumping out there. That was really close to our 5th harmonic, it looked like. But yeah, I can have changing numbers of these things, just as long as they're all in half wavelength intervals. So that exactly matched what we expected here. So I expected to see 1, 2, 3 little wave packets, which is exactly what we saw. So our third harmonic is matching. we don't discuss the weight of the bass string as well. Yes, we will discuss the weight of the string as well, and we will discuss the tension. So that leads us to some of our equations we're going to be using here. So we're going to see that some things are going to affect the speed of the wave on the string. So I'm not going to go through and actually derive this. What did you do to change this? So again, I just changed the mass that was hanging there. So that hanging mass, so the amount of mass I have hanging over the edge here, what is that affecting on this string? Tension. All right, so tension is going to be an important part of this. So the speed of the wave on the string, it's going to be a square root. All right, so I have tension. All right. Then we have the mass of the string. So the string mass does matter. So like someone was saying, what were we saying? The weight of the bass strings as well. So yeah, on any sort of stringed instrument, you have really thin strings with small mass, and then you have thicker strings with more mass. And if you look at the like violin and cello and the smaller instruments, they have much smaller strings. And if you look at a bass, they have a lot thicker strings. The other thing that matters is the length of the string. And if you ever forget the equation, just FML. So this is our FML equation. And how it's written on your formula chart. All right, so these are the things that we can do to affect the speed of the wave. We'll go through and do some calculations with this next class on your actual lab. Let me see if there's one I can actually do. We'll probably actually do one of them on your lab right now. Yeah, we could look at this. So doing some quick math. Let's turn you back on. This motor like absolutely kills these batteries, by the way. All right, so we can do some math with this. So I got this into the first harmonic. So see that nice, big, long wave envelope. So how we would start a question like this is we would go in, we would want to draw this. So I have right here, it goes up like this, down like this. How many waves do I have here?
Half.
I have half a wave. Right, a full wave would also do the down part. So half a wave is going to be equal to that length of the string. All right, so I measured the string to be 53.5 centimeters. 1/2 the wavelength is 53.5 centimeters. So what's our wavelength in meters? So 107 centimeters, or 1.07 meters. All right, so that's a wavelength that's happening on the string. So we know our wavelength. I don't know the frequency of this thing, and in fact, it's slowly changing as the batteries die over time. So we don't know our frequency, but we could try to figure out our speed. So let's try to put some things in for our speed. Speed is going to be the square root of, well, tension. I'm going to need to figure out our tension somehow. Well, that's based on our mass that's hanging down. Our mass is just sitting there hanging at rest. So I have tension holding this up and the weight of that hanger pulling this down. These are going to just sit there balanced. Now I can sit here and go through our numbers. Now, obviously, this thing has the mass of 2 dimes and 1 nickel, obviously. Yeah, we need the free body diagram for tension. All right, so the tension is equal to the weight. So we see our tension is going to equal mg. So I added 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 nickels. So our mass is going to be 18 nickels. But then we have 1 more nickel for the hanger, so 19, times the mass of a nickel is obviously exactly 5 grams. That's not even $1. 19 times 5 grams, but 5 grams is 0.005 kilograms. Plus, we have 2 dimes, which is 2.268 grams. 0.00268 kilograms. And this is all times 9.8 meters per second squared. Now, I haven't done the math yet, so someone needs to go through and do that. I don't have a calculator with me. I got 0.975 newtons. Did you multiply it times 9.8? I think that's it. It did not come out to that. So we have, I don't know if you can see that. We have 19 times 0.005 plus 2 times 0.002268, and then that's all times 9.8. Can I move the paper? Yeah. I keep trying to move it, but everything is backwards, and then it really messes with my brain. And you'd think that my brain would adjust to realizing everything's backward, but it just doesn't. Yeah, so you put the parenthesis here, you did this slightly wrong. Yeah, you put that parenthesis in the wrong place. I moved that very last parenthesis to in front of the 9.8. Yeah, that way you add the two masses together before you multiply times 9.8. All right. So is everyone able to get that? So we know our tension. All right, so I can put this in up here. We have a 0.9755 Newton tension. The string itself is 53 centimeters, 53.5 centimeters long. So the length is going to be times 0.535 meters. And then I got the mass of the string, but I need to redo that 1 second. Yeah, that was the hardest thing to get, was the mass of the string. And so, obviously, the mass of the string that's showing here is exactly 0.214 grams. All right, so how many kilograms is that? All right, MKS, meters, kilograms, second. All right, 2.14 times 10 to the negative 4. I'm just going to write that as 0.000214. That way people don't mess it up when they put it in their calculators. All right, so we can put this in here. So I have 0.000214 kilograms. So solve for the speed of the wave on the string. .38 meters per second. 49.38 meters per second. So when we do this, we see that this is not equal to the speed of sound in air. So anytime we're dealing with a string, we can't just use the speed of sound in air. It's going to be a very different value. All right, so we have our speed, 49.38 meters per second. I have my wavelength. What could I get from those two values?
Frequency.
Frequency. So speed is equal to wavelength times frequency, 49.38 meters per second, times, well, is equal to wavelength is that 1.07 meters times our frequency. And we're going to see our frequency is 46 point. I got 1.5 hertz because I didn't round to the last one. You divided 1.07 over, right? 49.38 divided by 1.07. So this is going to be a really common type thing that we do. With standing waves on a string, we're going to go through, figure out what harmonic we're in. So here we're in our fundamental harmonic. So the first thing first is drawing this out. So the entire length of the string is only making up half of a wavelength. And so we use that to get the wavelength so we can figure out our wavelength. So again, we have our new equation, our FML equation. It's on the formula chart. So we can substitute into that. We can use that to figure out the speed of the wave on a string. And this is what we're going to be doing in the next lab. We'll probably redo this. We're going to see that as these batteries change value, as I use them more, some values are going to change. So next class, we'll actually go through and do this activity, and we're going to see slightly different values. And then we can use that. We can figure out what the frequency is, or we can do several other different things. You're going to be doing a similar thing with your bottle, so not everyone has to make it set up like this. But yeah, we're going to be using the bottle to find speed of sound. So what we get? Yeah, you do have homework today. It's the second post should have it on there, right? Standing waves on strings homework. All right, so let's go through a few of those on the homework. What time is it? And let's try not to take too long on this. So everyone, if you can, try to pull up the homework. Do you do all of it for the homework? Yeah, I want you to try to do all of the homework. We will have tutorials tomorrow. So if you go to that, you can ask questions about the homework. So let's just start with our first one. Yeah, last meeting was just a tutorial. It was going to be class, but yeah, last week I was trying not to assign too many things, so I didn't get in trouble. So yeah, this week it's going to be kind of what we're going to do as long as we're at home. So as long as we're at home, we're going to be doing every other day we'll have a class in the morning at 10. And then on the days we don't have a class in the morning at 10, we'll have a tutorial in the afternoon. And that one will kind of move around based on the day. And so I'll try to post when those will be. So today, I think we have a meeting at 1. So I'll be doing a tutorial at 2 for my AP class. And then tomorrow we'll have a DC tutorial. I think that one's at 1. It should be on the thing. Yeah, the last one, the homework wasn't so hard though. So I wasn't expecting a lot of people. Yes, Kat? All right, we'll start with 1. Hopefully everyone can see this. If not, I'm going to read it out right now. So we have a 1.5 meter long rope. So we have the rope has a length of 1.5 meters. It's vibrated up and down with 33 complete cycles taking place in 10 seconds. 33 cycles in 10 seconds. This motion creates the first harmonic of the standing wave pattern. So the first thing you should want to do is to draw this out. On the test you will be getting, I will be making you draw this out. So you do need to draw it out. So first harmonic is pretty straightforward. It's like this. We've done this a few times, so just half of a wave. I only have the up part, I don't have the down part. So I have half of a wavelength here. And that's all equal to the length of the string. So half of the wavelength is equal to 1.5 meters. And that's normally how we're going to be starting these out. So A, draw the standing wave envelope. So we already did A. B wants us to determine the fundamental frequency. Well, fundamental is just another word for first harmonic. First harmonic, the other thing we can call this is the fundamental harmonic. And this is the lowest possible frequency that we can ever play on any instrument. So this is why taller people or larger people have longer vocal cords. The longer vocal cords are going to have a longer length, which means they can have a longer wavelength, which means they can have a lower frequency. And then shorter people are going to have shorter vocal cords, and so shorter wavelengths, and they produce higher frequencies. All right, so getting the frequency, that's probably something dealing with like 33 waves in 10 seconds. So frequency, is that the number of waves per second or the amount of seconds per wave?
Waves per second.
All right, so waves per second, frequency is going to be per second. Per second. So I have 33 waves in 10 seconds. Waves aren't really a unit we're going to keep, so we just put 33 happen in 10 seconds. So our frequency is going to be 3.31 over seconds, or hertz. All right, so that's my frequency. Now we already kind of started part C right here. We're getting 1/2 wavelength is 1.5 meters. So my wavelength, I can just multiply the 2 over times 1.5 meters. So my wavelength is going to be 3 meters. So wavelength for any of these standing wave questions, we're always just going to be looking at the length of the string itself, figuring out how many waves are there. And we're going to be using that to find what our wavelength is. All right, so once we do that, how fast is the wave moving? This is a little bit easier. Now that we have our values, we can just do speed is wavelength times frequency. So we have our wavelength of 3 meters, frequency of 3.3 hertz. So our speed is 9.9 meters per second. Yeah, that is D. Now, E. E is wondering what frequency the rope would need to vibrate to produce the first overtone. So what's the other word for first overtone?
Second harmonic.
First overtone is the second harmonic. How many waves do I add to get between harmonics?
Half.
So we're going to add half of a wavelength. So the first thing we should probably do is draw this out. So to go from here to here, I'm adding half of a wavelength. So how many waves do I have here? One. So yeah, we have one full wave. One wavelength is equal to the length of the string. So I know the wavelength of the second harmonic is just 1.5 meters. Now, speed, we just talked about our speed equation, the square root of tension times the length of the string divided by the mass of the string. Did I change the tension, mass, or length of the string? It doesn't say anything about changing those. So our speed is going to be the same. So if our speed is the same, I can just use the same value from here. So speed is equal to wavelength times frequency, or that 9.9 meters per second is equal to 1.5 meters times the frequency of the second harmonic. The 1.5 meters is the length of the string. So the string's length is 1.5 meters for both of these. All right, so I get 6.6 hertz. Now, this looks pretty similar to this. The frequency of the first harmonic was 3.3 hertz. The frequency of the second harmonic is 6.6 hertz. What multiple is this of that? Two. So frequency of the second harmonic is 2 times frequency of the first harmonic. That's interesting. This is n equals 2. Let's see what happens for F. Not 1/3. They're multiples of 2, or you could say half. F wants to know the period of oscillation for the sixth harmonic. All right, so we're going to draw this out. This is going to be a little messy. 1, 2, 3, 4, 5, 6. We still have the same length of string, 1.5 meters. Again, we didn't change our tension. It said nothing about changing the mass of the string itself. And so we have the speed of the string is still going to be 9.9 meters per second. But now how many waves do I have here? 3. And again, each time we're adding a half wavelength, right? So here I have 1 half wavelength. Here I have 2 half wavelengths. Here I have 6 half wavelengths is equal to the length of the string. or 3 wavelengths is equal to 1.5 meters, or the wavelength of that 6th harmonic, 1.5 divided by 3 is 0.5 meters. All right, so I have my wavelength, I have my speed. So the speed of that wave is going to be wavelength of the 6th harmonic times frequency of the 6th harmonic. 9.9 meters per second equals that 0.5 meters times frequency of the 6th harmonic. So what's our frequency? 19.8 hertz. All right, so for this one, we're on n equals 6. How much times our first harmonic frequency is 19.8? 19.8 is what times 9.9? Not 9.9, I mean. 19.8 is what times 3.3? Sorry, I misspoke. So the frequency of the 6th harmonic is what times the frequency of that first harmonic? That's exactly 6 times. So I see 6 times the frequency of the first harmonic is equal to the frequency of the 6th harmonic. Here I saw the frequency of the 2nd harmonic is 2 times the frequency of the first harmonic. That's kind of nice because I could just say instead of 6, I could call these values n, right? N equals 6, n equals 2. So I could say n times the frequency of that first harmonic is equal to the frequency of that nth harmonic. So how would I get the frequency for the 100th harmonic? Multiply the first harmonic by 100. So the frequency of that 100th harmonic would just be 100 times the frequency of the first harmonic. 100 times 3.3 hertz. So the frequency of the 100th harmonic would be 330 hertz. And so on. So a lot of these are series solutions. So there's a lot more series that we can get out of this. I'm not going to go through every single one of them, but this is just one that can help you out really fast. And then the other thing I forgot to mention, so here we have our 6th harmonic. Which overtone would I call this? So 6th harmonic, that means I have my first, but then I have a 2nd, 3rd, 4th, and 5th, and 6th. So this is going to be the 5th time we resonate after that first harmonic. Any questions about anything I did on this number 1? No questions? All right. So let's look at 2. Try to start number 2. Again, the first thing you probably want to do is try to draw out some sort of picture on the 3rd harmonic. So think about how many half wavelengths we have for that 3rd harmonic. All right, third harmonic. So how many of those little packets do we have? How many of those little things do we have here? So starting here, ending here. Three. So we have three of those half wavelengths. So I go up 1, 2, 3, and then it bounces back and forth around these points. And again, I have 1, 2, 3 of these antinodes. These are the things that are bouncing around really fast back and forth. And then I have 1, 2, 3, 4 of these nodes. Nodes just don't even move at all. So destructive interference where the waves cancel out, and then constructive interference where the thing shakes back and forth really fast. All right, so I have 3 of these little half wavelength packets like we've seen before. The only thing I'm allowed to add are these half wavelength packets. So I know I have 3 half wavelengths is equal to the length of the string. And again, this is how you're going to be starting pretty much every single one of these. Draw a picture, figure out how many wavelengths I have in there, and relate that to the length of the string. All right, so 2A wants us to get the frequency of oscillation. So again, how am I getting frequency? Waves per second or seconds per wave? All right, so yeah, waves per second. So number of waves per second is equal to our frequency. All right, so I have 6 meter long. Each wave is produced every 0.2 seconds. So I have one wave, right? Each wave means one wave every 0.2 seconds. So we have a 5 hertz wave. And then this is the frequency of the third harmonic is 5 hertz. All right, B wants us to get the speed of the wave. Well, before I can get the speed of the wave, I'm going to need the wavelength of the wave, right? Speed is wavelength times frequency. Well, I know I have 3 of these little half wavelength packets, so 3 of those half wavelength packets is equal to the length of the string. So 3 halves wavelength is equal to the string is 6 meters long. 6 times 2 is 12. 12 divided by 3 is 4 meters. So I have my wavelength of the third harmonic, I have my frequency of the third harmonic, and I just have to multiply these. Four times 5 is just 20 meters per second. All right, so C wants us to know how often would I need to produce, how often would a new cycle need to be produced to generate the 8th harmonic? Now, we have the long way of solving this and the short way. Let's do it the long way first, right? Because we're having so much fun right now. Who wants to do it the easy way? See, no one's responded immediately. No one wants to do it the easy way. All right, so first of all, what are they asking? How often would a new cycle need to be produced? Obviously. Easy is boring. So how often? What value are we actually trying to solve for? Frequency, right? Yeah, how often is, let's say, how often does a day occur? Well, a day occurs once per 24 hours or once per 86,400 seconds. So, how often something happens? I wake up once per day. So, often is talking about frequency. So, frequency is what we're ultimately trying to find. Now, we didn't change anything about my string or anything. So speed is the square root of that tension times length divided by mass. It said nothing about changing anything on our string. In fact, I don't think you even use the string equation on here. We'll use it in our lab, but I don't think any of these questions involve the string equation. All right. So we have a constant speed. So our speed on that string is still going to be 20 meters per second. Now, eighth harmonic. So let's draw this out. We have 8 up and down. So 1, 2, 3, 4, 5, 6, 7, 8. And then we can draw that reflected wave. So 8th harmonic is the 7th overtone. This still has the same length. We're still, what was the length before? 6 meters long. But how many half wavelengths do I have now? One, two, three, 4, 5, 6, 7, 8 half wavelengths. So I have 8 half wavelengths is equal to the length of the string. 8 halves is just 4 full wavelengths is equal to 6 meters. So my wavelength is going to be 4/6, which is the same as 3 halves, or 1.5 meters long. So this is the wavelength of the 8th harmonic. I know the speed, so speed is going to be wavelength of that 8th harmonic times the frequency of the 8th harmonic. 20 is equal to 1.5 times frequency of the 8th harmonic. Divided by 1.5, you're going to get a not so nice repeating fraction. .33 hertz. All right, so that was the longer way where we had to draw this out and go through all that. What's our faster way? There is a faster way. Well, I know frequency of the nth harmonic is n times the frequency of the first harmonic. So frequency of that third harmonic we solved for at the beginning is 3 times the frequency of the first harmonic. So our third harmonic was 5 hertz, is 3 times the frequency of the first harmonic. So our first harmonic has a frequency of 5 third hertz. Not by the original, but by the first harmonic. So we need to get our first harmonic first. And then the frequency of that 8th harmonic is 8 times the frequency of the first harmonic, or 8 times 5 thirds hertz. Oh, yeah, you're right. And then so I have 8 times 5 is 40 divided by 3/43 hertz, which is the same as 20 divided by 1.5. And then if you're even lazier than me, as lazy as I am, I mean, I would have just done 5 divided by 3 then multiplied it by 8. But try to be correct over being lazy. Also, we are going to have a test on this next week, probably middle of the week. I'll get your review to you by the end of the week. It is going to be randomized, so don't just expect to be able to text someone and ask for all the answers. So I have a fun way of randomizing all of the questions. All right, any questions on the second one? I would say this is kind of like everything we've been doing on the lockdown. Everything that we've been doing on this, where the math isn't so hard, but there's kind of a lot of random things. Yeah, it's only going to be free response. I'm not going to do any multiple choice. I'm not going to mess with that. So it will only be free response. The test will cover just simple properties of a wave and calculations with the wave. And then it's going to have some intensity type questions, like watts per meter squared, things like that. You'll have a Doppler effect question and standing waves on a string, like what we're doing now. So yeah, one more way through that. So just waves, simple wave equations, and measuring things about a wave, intensity, Doppler effect, and standing waves on a string. So it's a little bit focused. We're cutting down the unit just a little bit. There's some more complexity to it, but I'm not going to go way too in depth. Partly because we're ahead of Miss Chuma, and then partly just because it would be rather painful to teach you the other types of standing waves and air column. That gets a lot messier. Let's see. What was a hard one? 3, 4 is kind of easy. 8, 9. I'll let y'all choose one. Go through and find me one to do. Except for 12. I want y'all to try 12 on your own. So I'll do one more, find me a random one to do, and I'll do it. Try to find one that you think is difficult. Because these all pretty much ask similar things. Actually, no, let's do 13. I take that back. 13 is good. Yeah, I want y'all to try 12. Just think about how many waves it is. The hint, it's not easily split up into half wavelengths. So just how many waves do you have for number 12? So you have half a wave here. But how much do you have here? Is that a full half a wave? Yeah, that's half of a half, so that's a quarter of a wavelength up here. So a half plus a quarter is 3/4. That's the only really hard part about that. It's just using your 3/4 of a wavelength. So let's do 13. All right, so 13, I'm pretty sure they intended to say the word slinky. A standing wave is established in a slinky, as shown in the diagram to the right and down. The distance from A to B is 4.69 meters. So A to B that length is going to be 4.69 meters. How many waves do I have between A and B, though? So just between A and B, how many half of those waves do I have? Yeah, 3 half wavelengths. So 1 half, 2 half, 3 half. So I have 3 half wavelengths is equal to that 4.69 meters. All right, so already that fast we can figure out a wavelength. When not being vibrated as a standing wave, a single pulse introduced into the medium at point A will travel to the opposite end and back in 2.7 seconds. Determine the vibrational frequency of the wave pattern. All right, so let's ignore that second part for now. Let's just use this to figure out our wavelength, because ultimately we're trying to figure out the frequency. So we're probably going to be doing speed as wavelength times frequency at some point. So we still want to get our wavelength. What's our wavelength equal to? Multiply the 2 over, so 3 times the wavelength is 2 times 4.69 hertz. Yeah, 3.13. We're in a middle step, so I'm going to keep one more decimal place. I'm going to say 3.127 meters. 3.13 would work just fine. All right, so I know my wavelength. We're trying to find frequency. So that means I'm going to have to find speed. But I can't use this equation to find speed because I'm trying to find frequency. So what equation am I going to use to find speed? Yeah, speed is distance over time. All right, so I know my time is at 2.7 seconds. Distance is a little bit messy here. The distance, 4.69 meters, right? The wave travels 4.69 meters?
It goes forward and back, right?
Forward and back. But is that forward and back just 4.69 meters, though?
It goes past point B.
It goes past point B. So we have this. We have 1, 2, 3, 4, 5 half wavelengths here, right? Because B stops here, A is here, and then this is where it's attached to the tree. So I go 1, 2, 3, 4, 5 half wavelengths, right? 5 half wavelengths is equal to the length of the string. So the length of the string is 5 halves times our wavelength is at 3.127 meters. So the string is 7.817. I rounded a little bit less, so I got a 5 at the end of that. 7.8175 meters. All right, so the wave travels 7.8175 meters only, right?
Goes forward and back.
Goes forward and back. So now we're to that forward and back point. Now the distance traveled is going to be 2 times the length of the rope. So we can multiply that whole thing times 2. So the wave actually travels 15.635 meters. Now we can finally put that distance in here. I'm probably not going to mess you up with that many ratios like that. There's plenty of other things I can mess you up with that deal with physics, not just the math. And yeah, we end up with a speed of 5.791. Still an intermediate step, so I'm going to keep one more digit than you. Meters per second. All right, now we're almost done. Now I can finally put this in here, 5.791 meters per second is equal to, we had a wavelength of 3.127 meters, but we don't know what our frequency is. Yeah, 1.852 hertz. All right, so I think most of this is relatively straightforward. Obviously, it's the first time doing it, so I expect questions. I think I set this homework to be due not tomorrow, but the day after tomorrow, so Thursday at midnight, something like that. If you have any quick questions on any of these, otherwise, tomorrow, what time did I say is tutoring tomorrow? I posted that in the stream, the 2-week schedule. And if we're here longer, I'll post another one. Thanks, you won't let me pull it up. Well, it's not letting me pull it up. What the heck is happening? Is this not connected to the internet? I'll be right back. Well, everything seems to think that my internet is down except for my iPad, so whatever. Yeah, I forget the time. I'll post a link telling you the time if it changes from the schedule. But yeah, sometime tomorrow afternoon, either at 1 or at 3, we'll have tutorials. So yeah, work on this. This will be due 2 days from now. Other things due today, your warm up from last class, the take home test. Take home quiz. I think I put due yesterday. Get those in, warm up, things from last class. Any questions about homework or the class or things in general? Yeah, we are having a lab next class. You can look at the activity. So we're going to be gathering data from that, and then you'll make predictions, and we'll actually test your predictions. And then the other thing, the warm up is still on YouTube. Yes. I put some of the things to unlisted because I was trying to link them, but people were complaining, so I put it back to public. So yeah, everything's still on YouTube. How are you going to work as groups? So I do still want you to try to work with groups for your lab. What you can do, you can either collaborate through like a group phone call or something. You can also, I'm pretty sure you all have access to Google Meets. So you can get your own one of these that I'm using right now. It's actually pretty easy to do. Just just open up Google, click on the 9 boxes on the side, and you should have a thing for Google Meet. And you just start a meet, create a name, and then you just send people the name of the group, and they can join really easily. This is probably one of the easiest things I've ever used. So yeah, I do want you to try to do groups for your lab because this might be a while. And partly I still want you to try to collaborate, partly what's that? Oh yeah, my when I look through it, it is a mirrored image. If you're looking at your face, so I can actually turn this around. There's like 3 buttons right there, and I can switch my camera, and then I can see you. And this isn't mirrored. I don't think it's mirrored. Yeah, this isn't mirrored. Actually, it is, but it's mirrored correctly because it's looking at me. You get used to it though. I have it pulled up on another computer, and I look at that as opposed to my iPad screen, which is why you might see me on here 2 times or 3 times. Yeah, I'm connected on here as 3 different people. There are 3 of me, or just 3 different electronic devices connected to it. It's actually, I have my iPad, iOS, I have my Linux computer connected, and I have a Windows computer connected. So that's fun. All the technologies. I'm working on it. Any other questions? I do like PC. I do also like consoles. They allow like people to like who can't build their own computer to have it. They're a low cost entry into gaming. I will say if you try to put together a really cheap computer, it's going to be worse off than a console. Any other questions? If there's no questions, I'm going to stop recording.